Okay, I wanted to go over quickly the solutions to exam 2 here. Alrighty. In this problem, number 1 here, we were given a certain matrix, okay? 1x, x squared, 1y, y squared, 1z, z squared. Okay, reading across there. So we've got that 3 by 3 matrix, and we were attempting to find its determinant. Okay, if you followed my hint there, I said go ahead and use some row reduction operations and facts about determinants to get a simplified formula, okay, rather than just doing the regular expansion technique. Okay, well, if we go ahead and look at the matrix inside the determinant here, you notice that we've got 1, 1, 1 here in the first column here. That's kind of wonderful. If you think about row reduced echelon form, I've got what? A 1 right where I want it, okay? So the first thing to do is here I'm going to perform a row reduction inside the determinant symbols here, the vertical bars here. Remember, under such a row operation, a multiple of one row added to another row, or a multiple of one column added to another column for that matter, will leave the determinant unchanged. That's going to justify my equal sign here. Okay, so I'm going to go -1 times the first row added to the second row, and I'm going to go -1 times the first row added to the third row. So the first row is unchanged. The second row becomes 0, y minus x, y squared minus x squared. The third row, 0, z minus x, z squared minus x squared. Okay, and then those two will be equal. Now you notice here in the second row here, that's y minus x. Y squared minus x squared actually factors as y minus x times y plus x, and a similar statement can be made here for the third row here. So in the second row, I'm going to go ahead and do what? I'm going to factor out y minus x. Now remember, if I've got a multiple from a single row or a column from a determinant, I can factor that right out of the determinant, right? That particular factor. So here I've got 1x, x squared, 0, 1, y plus x, or x plus y if you prefer. And then what? When I factor out the z minus x here, I've got 0, 1, z plus x with those factors on the outside of the vertical bars. Okay? Now, once again here, I'm going to use row reduction here. I see I've got what here? If I'm imagining row reduced echelon form, I've got a 1 right here in the second row, right where I want it. So if I use this as a pivot here, I'll go -1 times the second row added to the third row, and leave the rest unchanged here. And then I would get here, what? Z minus y and zeros in these places, okay? And now, notice this is what? An upper triangular matrix here. The determinant of our upper or lower triangular matrix is just the product of the main diagonal entries. So that's 1 times z minus y. Put it all together. The answer is y minus x, z minus x, z minus y, and there is the determinant. Okay, by the way, there's a name for this type of matrix here, or the determinant thereof, a Vandermonde determinant, or a Vandermonde matrix. You can see that this can actually be used, what, in polynomial interpolation. Okay? Anyway, so we've got this nice formula here. When is M going to be invertible? M is going to be invertible if and only if its determinant is non-zero, right? Since that's a square matrix. And when is that going to happen? That's going to happen precisely when each of these factors is non-zero. And those factors are going to be non-zero when what? X and y and z are all different from each other. Okay? So that's the answer to problem 1 here. All right. Let's take a look at problem number 2. This is just very simple. This is actually testing your knowledge of things like determinants of echelon upper triangular matrices and lower triangular matrices. I've got an LU decomposition here. Okay, the determinant of A should be the determinant of L times U, but remember the determinant is multiplicative, right? So that means it's the determinant of L times determinant U. Determinant of L, remember in an LU decomposition, the main diagonal are all going to be 1s. So that determinant is going to be the product of those 1s, which is 1. Okay, So it's actually going to be what? The determinant of the upper triangular matrix, the echelon matrix here. So again, we mentioned here the determinant of an upper triangular matrix is just the product of the main diagonal entries. So that's 1 times 8 times negative 2 times 4. I got negative 64 for my answer here. Okay. In number 3, I created a little definition here. I called it cyclic. Different people have different answers to this, I have no doubt. A matrix is cyclic. What? If some power of the matrix, some natural power of the matrix is what? The identity, the multiplicative identity. So some natural power of the matrix is the multiplicative identity. Okay, the natural numbers, just to remember, don't include 0, and the natural numbers are technically 1, 2, 3, 4, 5, 6, baby numbers you first learned. Okay, there's various answers on this one. I'll just give you an example of what I did. Is this matrix reading across 0, 0, 1, 1, 0, 0, 0, 1, 0. Do you see how I actually got this matrix? Okay, you can see what I did. I messed with the identity, right? Messed with the identity matrix. Okay, well, give that a little thought. So I took this one and I went, what? Its square ends up being, you can see, what? This matrix, which is not yet the identity, but its third power is the identity matrix. Okay? It's the identity matrix. So that was the example I came up with, just a certain permutation of the rows of the identity. Okay? So that's one example. You might have had a different example. If A is a real matrix and of order 3 in its a cyclic matrix of order 3 here, so I cubed is, or A cubed is I, then what's going to happen is the determinant of A cubed is going to be the determinant of I, all right? But the determinant of a product of matrices is the product of the determinants, so I can actually bring the power 3 on the outside. So I've got the determinant of A cubed is 1. Now, since A is a real matrix, only has real entries, the determinant of A must also be real. Okay? So imagine the equation D cubed equals 1, and you're only looking for real solutions. The only solution would be what? D equals 1. So you've got determinant of A is going to have to equal 1. Okay, so there's number 3, double I. Okay. Now let's just assume that if A is allowed to assume complex, non-real, okay, let me emphasize this, non-real entries, then the determinant of A could also be complex then, obviously. Okay? It's not necessarily real. Okay, I just went ahead and let D, cap D, equal the determinant of A. Then look at this equation again. D cubed equals 1, just like in part 2. But this time you want to think about the fact that D might take on complex values. Now let's go ahead and set this to 0 like usual. And then we're going to factor this. So it's D cubed minus 1 is equal to 0. Factor out D minus 1. The other factor is D squared plus D plus 1 is 0. If I'm interested in all zeros here, all right, all zeros of this polynomial, then I take each factor, set it to 0. The determinant could be 1, or the determinant could satisfy the second equation, D squared plus D plus 1 is 0. If you go ahead and use the quadratic formula on that, you get negative 1/2 plus minus the square root of 3 over 2i. Okay, so there's actually 3 possibilities here for the determinant of a complex matrix that has order 3, a cyclic matrix of order 3. Okay, number 4 was fairly straightforward here. I've got x cosine t minus y sine t is 5t, x cosine t plus y sine t equals 2t. I asked you to use what Kramer's rule on this. So you're going to do what? Denominator, you're going to take, since x and y are the unknowns, okay, you're going to take the determinant of the coefficient matrix. So that would be the determinant of cosine t minus sine t, cosine t plus sine t. Okay? And now since you're looking for x, remember how the method works, you're going to replace the coefficients of x here by what? this column vector, 5t, 2t, don't forget that's a determinant also. Take those determinants and work them out, and I think you get 7t sine t, and down in the denominator 2 sine t cosine t. The sines cancel, and 1 over the cosine is the secant, so I wrote 7/2 t secant t. Okay, y is similar here, only you're replacing what? The row of, or the column of coefficients on y by 5t, 2t respectively, and I got -3/2 t cosecant t in the end. Okay? Alrighty. Number 5, I asked you to use the adjudicand to find the inverse of this particular matrix. Notice I was somewhat benevolent. This is actually a pretty easy matrix here, and hopefully in the end you notice something about the inverse in the end. First thing you wanted to do was find the determinant of A, right? Now that's easy to do. You either expand across the first row or first column, and you're just getting 1 times what? The determinant of this submatrix here, this minor. Okay, and I got this. I got a determinant of 2. Okay, so that's what I did. Okay, the inverse. Okay, A inverse should be the reciprocal of the determinant of A times the adjudicand of A. Okay, remember how to compute the adjudicand here? Oops. You know what I forgot on this? Although I did it over here. Was I forgot to include the, I like to put in the transpose in there when I write it out. But anyways, I already took the transpose on this thing. So what you do is what? We just compute all the what? Subdeterminants that you can here. Don't forget to include what? The appropriate signs on each of these, right? To get the adjudicand, and take the transpose in the end. And what can I say? This is what I got in the end. Kind of a long calculation here. You can always double check your answer. I hope you did that by what? Just multiplying these two matrices together, and hopefully you get the 3x3 identity, right? Okay, that's what I did, and I think it works. Okay, I think it worked for us. Okay, this is what I got. See if that's what you got. Oh, what was number 6? Oh, one comment about this one. Did you notice in the end, the inverse of A ended up being what? 1 with zeros in this row and column. This part right here is actually the inverse of this, what? Submatrix here. Okay? You might have guessed that was actually going to hold. And it did. Okay, let's go to number 6 here. Number 6 was talking about finding the area of a triangle. Okay? Now, there's a couple ways to do this, but here's the way I chose. Okay? I've got find the area of the triangle with these vertices, -1, 2, 4, 7, and 6, 21. Okay? The vector from -1, 2 to 4, 7 is, sometimes I like to do this, it's called the point difference, okay, which ends up being a vector, okay? In Calc 2, we would have used angled brackets here. I just chose to, by the way, this time, chose to just write it as a row vector for a change, okay, just to show you that you can do that. You could just as easily, and I do in other problems, just write that as a column vector if you'd rather. You know it's not going to make any difference in the end. Okay, but anyways, from the first point to the second point, that yields that vector 5, 5. From the first point to the third point yields the vector 7, 19. Then what you can do to find the area of the triangle formed by these is this, and then I suddenly realized I got this wrong. Okay, area of the parallelogram is 60. Area of the triangle, I said triangle, isn't it? Area of the triangle is half that, so that's going to be 30. Okay, yeah, but basically what do? You just take the determinant, and that will give you the area of the parallelogram formed by these two vectors, okay, with the parallelogram law of addition. Okay, if you want to form the whole parallelogram. For the triangle, though, you're just going to take half of that then. Okay? If this turned out to be a negative number, what did you do? Just take the absolute value, right? If it turned out to be a negative number. Alrighty. Let's come back to this one. Okay, what was number 7? You're just trying to find a parametric equation for the line between 2 points, 1, -3,2, and 4, 7, 9. Use length as a parameter, okay? Remember arc length, we use S, okay? Here's what you want to do. I just did it this way. I had the starting point being 1, -3,2, and the end point being 4, 7, 9. Remember, length is actually directed length, so it can assume negative values. Then when I take the point difference here this time, I decided to just, for the sake of variety, write it as a column vector instead. Okay? But you could do it with a row vector if you'd rather. That'd be more like what we did in Calc 3. Okay, find its magnitude. Okay, and I got the square root of 158. Okay, now the position vector of any point on the line x, y, z is the position vector of the original point 1, -3,2 plus arc length s divided by 158 times 3, 10, 7. Do you understand that you're going to have to actually use what? What I'm actually using is p hat, p divided by its own magnitude, p hat here. Okay. Otherwise, your parameter would not represent length. Okay, it would not represent length. So your p here, the vector parallel to your line, better be a unit vector if you're going to be using arc length. Okay. Then I simply broke that down into what separate values of x, y, and z here in terms of s. Kind of looks like a 5. That's supposed to be an s, though. Okay. All right. Whatever. Okay. Projection. This turned out to be very easy. Do you remember how to project one vector onto another? You take the dot product of the vectors divided by what? The dot product of the vector you're projecting onto down in the denominator times the vector itself. Okay. When you do that, you notice they both have dot products being 5. So the actual vector projection ends up being the vector v itself. Okay, and 9, find the equation of a plane normal. Okay, you want the normal form. ax plus by plus cz equals d. The plane contains these points 1, 0, 3, 2, 1, 1, and 5, -2, 7. So what I did was go ahead and form the vectors from the first point to the second, from the first point to the third. So I got 1, 1, -2, 4, -2, 4. I took their cross product. Okay, I got 0, -12, -6 as a column vector here. This is a normal. What's a better normal? Well, I can factor any factor I want out of this. I could make this a unit normal if I wanted to, but I'm not going to. I just factored out -6 here. 0, 2, 1. That would be a nicer, neater normal. Okay, now if x, y, z is any point on the plane, then the vector from our original point 1, 0, 3 to the point x, y, z would be x minus 1, y minus 0, z minus 3. The dot product of that vector with the normal must always be what? 0. When you do that and actually work out the details, I get 2y plus z equals 3 for my answer. So it's a set of all points x, y, z plus 2, such that 2y plus z equals 3. Gaussian elimination would be another method. Okay, it would be another method that you could have used on this if you wanted. You know, you've got the 3 points that lie on that. Okay. I didn't choose to do it that way, though. Okay, for which value of x would these vectors, for which value of x here, would these vectors not be linearly independent, that is, linearly dependent? Okay? Okay, so what I said here, these are going to be linearly dependent if and only if w vector is some linear combination of u and v. In other words, it lies in the span of u and v. Okay, that would mean there exists scalars alpha and beta, such that alpha u plus beta v is w. Let's go ahead and write that as an augmented system here. So we'd have 1, -1, 1, -2, 3, -1, 3, 5, and x. Okay? Then I went ahead and row reduced echelon form. Row reduction would be enough to actually answer the question, but I went the whole way for a double check here in just a second here. So I went RREF. So we got 102, 011, 00, x minus 11. This is going to be a contradiction, right? You would have 0 on this side unless x is what? 11. If x is 11, then you've got 0 on this side, and there's no contradiction. So we've got to have that what? X is 11. Just for a double check here, you see that this implies that what? Alpha is 2 and beta is 1. Let's double check here. Suppose I put in 11 for x and let alpha be 2 and beta be 1. So that would be 2u plus 1v. So that would be 2 negative 4, 6 plus negative 1, 3, 5. And you would get what? 1, negative 1, 11. Okay? Perfect. Okay, so it worked. Okay, so there's the answers to those problems. I also gave you a PDF copy. Beware of that one problem where I forgot to take half of that. Just notice that I said triangle. Okay, but there it is. Okay, have a good day.